Generating is a term used to explain the development of a line or surface. A point moving through space generates a line, and a line moving through space generates a surface. In mechanisms, a great variety of surfaces is employed, but in the following we consider principally those surfaces used in connection with gears for transmitting motion. When it is required to transmit rotation from one shaft to another at a definite ratio, with the shafts rotating in opposite directions, several means can be employed. One method is to employ friction discs. Pulleys of the same diameter ratio as the friction discs and connected by a crossed belt can be used. But to transmit uniform angular velocity, properly designed and generated gears present the most satisfactory solution. Friction discs cannot be relied upon to transmit uniform angular velocity because they lack positive driving contact. As soon as sufficient load is imposed upon these members, slippage between the discs occurs. Crossed belts are more dependable than friction discs, but here again, because of the lack of positive driving contact of the belt on the pulleys, when sufficient load is applied, belt slippage occurs, and uniform angular velocity cannot be maintained. Gears offer the most practical means for transmitting uniform angular velocity, but the shape of the teeth has an important bearing on smoothness of the transmitted motion. The involute is the most practical tooth shape for transmitting smooth, uniform angular motion. The involute, in this case, is that curve traced by a point on a crossed belt as it moves from one pulley to the other without slippage. Templates are attached to both pulleys. Now observe the movement of a point on the crossed belt. As the belt moves from one pulley to the other, the point on the belt traces involute curves on both templates. If these templates are cut to the traced curves, they produce mating involute profiles which will transmit uniform angular motion when the connecting belt is removed. Since each of these profiles is only one side of a single involute gear tooth, they will only transmit action through a slight arc of rotation. To transmit continuous uniform angular motion, succeeding, equally spaced, and parallel profiles must be provided so that a succeeding pair is in position before the preceding pair leaves contact. If motion is to be transmitted in both directions, then similar profiles must be provided. These gears fit the center distance as the original friction discs and pulleys. By superimposing the original friction discs, it will be noticed that they are the pitch circles of these gears. Likewise, the pulleys are the base circles, and the crossed belt represents the line of action. Where this belt crosses the line of centers is the pitch point, which is also the tangent point of the friction discs. As soon as a load is applied, it will be noted that only the gears are transmitting uniform angular motion. The friction discs and crossed belts are both slipping. A cardinal virtue of the involute is that it permits a change in center distance without affecting the velocity ratio or conjugate tooth action. When center distance is changed, the base circles remain the same. But a new line of action is created. A pitch point at different radii and new pitch circles. All these elements, when located at the short center distance, are shown in full lines, and the same elements in dotted lines when the center distance is increased. When the center distance is increased, contact takes place further out on the involute profiles. A study of the action of mating involute profiles shows that they slide upon each other for their entire contact. Here, both base circles are divided into an equal number of spaces, and tangent lines are drawn from the division points to the involute profiles. Note that sliding takes place and that the rate of sliding is greatest when the end of one profile contacts its mate in the vicinity of the base circle. We will reinsert our original crossed belt to illustrate that these division points on both involutes, when they make contact, lie in the common tangent to the base circles. This is the line of action. When the center distance is increased, the rate of sliding is not as great as before, because contact takes place farther away from the base circles. This condition is seen clearly in this close view. The parent rack of the involute system of gearing has straight sides. Here, the involute template is driving the rack with uniform linear motion. When the involute template has traveled distance x along the line of action, the rack has moved distance y. A similar movement of the template will carry the rack along a similar distance y, thus indicating uniform linear motion. With properly designed and generated involute gears, smooth, continuous action results. But improper design can defeat the attainment of this objective. A condition known as involute interference is sometimes encountered when the teeth either lock or will not pass smoothly through mesh. Free rotation is prevented because the teeth on the large gear extend beyond the point of origin or interference point of the profile on the mating pinion teeth, resulting in premature contact. This close view shows that the outside diameter of the large gear extends beyond the interference point, and hence the teeth will not pass through mesh. Involute interference can be avoided in several different ways. One is to design the cutter to remove the interfering portions of the pinion teeth. A paper template of the original pinion located behind this undercut pinion clearly shows the alteration. The change in shape of pinion tooth reduces its strength and removes a portion of the involute near the base circle. If the same center distance and tooth ratio must be maintained, another method is to enlarge the pinion diameter and reduce the gear diameter a proportional amount. This slightly reduces the length of involute profile on the gear tooth and increases the strength of the pinion tooth. Another method is to increase the pressure angle, maintaining enlarged and reduced diameters. This improves gear action by lengthening profile on gear tooth. In some cases, an increased pressure angle alone enables standard blank diameters to be used. Another condition, fillet interference, here exaggerated, results from the fillet interfering with the tip of the mating tooth. This prevents the transmission of uniform angular velocity. A paper template of this gear with the high fillet placed behind a properly generated gear shows the amount of material that had to be removed to avoid fillet interference. This is a diagram of a pair of gears, the teeth of which have been shortened to the extent that they lack continuous action and will fail to transmit uniform angular velocity. Here is the actual length of contact of these gears, and here is the minimum length necessary for continuous action. This condition is clearly shown here where the gears are superimposed on the drawing. As these gears are rotated, observe the points where the teeth start contact and where contact ceases. In properly designed gears, the line of contact should be of sufficient length to ensure continuous action. This pair of gears meets this requirement. Any member carrying a load is subjected to stress causes deflection. Here, a beam is stressed by an imposed load. The light flare indicates the location and intensity of the stress. If we cut a notch in this part, it will be noted that the point of greatest concentration of stress has changed. In order to show the nature of gear tooth action, straight polarized light is employed. The tangent points of contact of the teeth on the line followed by noting the travel of the points of light. Here we are observing a pair of accurate gears. It will be noted that the intensity of the stress of teeth comes into contact. By increasing the load, the stress is intensified. A common error is eccentricity. If the amount of eccentricity between gears is sufficient to prevent free rotation, then a wedging action takes place between the teeth, creating concentrated stresses when the gears are in the position of greatest eccentricity. By increasing the center distance to avoid this wedging action, the stresses are greatly reduced. These gears have been purposely cut with an excessive amount of eccentricity to illustrate this condition. It will be noted that the stress still increases slightly when the gears are at the high point. Variations in tooth spacing cause a change in velocity ratio, resulting in an unequal concentration of stress due to the intermittent tooth action. Note that while the stress is fairly light on one tooth, it is increased on the other, this being caused by a slight wedging action due to the displacement of the teeth. These gears have been cut with different pressure angles and consequently do not provide conjugate action. The result is indicated under light loading conditions. Tooth contact does not start at the tip of the tooth on one gear and hence falls short of complete profile contact. With an increased load, contact extends to the tops of the teeth on both gears, but the intensity of the stress varies. Gears are sometimes cut off pressure angle to compensate for deflection under heavy loads. Here, the teeth are shortened to cause lack of continuous action. This prevents the transmission of uniform angular velocity as indicated by unequal stress concentration. High speed causes vibration and increases stresses. When fillet interference is present, stress concentration takes place at the root of the gear teeth with the high fillets. This causes an interruption in involute action and at high speed results in noisy operation. Polarized light here reveals the nature of the tooth contact between spur gears. Note that the line of contact occurs instantaneously across the entire face width of the teeth. This line of contact moves up and down the profiles as the gears are rotated and demonstrates that smooth, uniform angular motion results because a succeeding pair of teeth takes up the load before a preceding pair passes out of engagement. It is interesting to observe the variations in width of the contact lines as the gears rotate. the width decreasing as contact approaches the pitch circles. Here the load on the teeth has been greatly increased. It will be observed that the contact lines are no longer of an even width from one end of the teeth to the other, but vary due to the heavy loading and the plasticity of the lucite material. It will also be noted that the nature, location, and intensity of the stresses change with the contact positions of the teeth as the gears rotate. When the point of one tooth contacts the flank of its mate, the stresses are shown to be of greatest intensity. Straight polarized light is here applied to illustrate the nature of the tooth contact between helical gears operating on parallel axes. The line of contact is at an angle relative to the axes of the gears and travels progressively across the faces of the teeth when the gears are rotated. In helical gears, if the advance of the helix in the face width is equal to the circular pitch, the gears possess continuous helical action. Helical action means that there is progressive pitch line contact occurring continuously across the faces of the teeth. For this reason, helical gears, when properly designed and accurately generated, operate more smoothly and quietly than spur gears. We will now show applications of the generating principle to gears and other shapes. Here a cylinder is being generated by a single point tool. While the tool is reciprocating, the work is rotated at a definite rate of feed. In generating an elliptical surface, the work rotates and the center distance between tool and work changes in timed relationship to the rotation of the work. This same principle of generating with a single point cutting tool is here shown applied to the cutting of a cam. A single point reciprocating tool is shown here generating a plane surface. The work remains stationary while the tool is moved along at the required feed. Generating is here applied to cutting a spur gear. A cutter in the form of a gear with relieved cutting edges is reciprocated and rotated in harmony with the work. In cutting helical gears, a twisting motion is imparted to the cutter as it reciprocates and rotates in harmony with the work. Here is an irregular shaped part which is generated on the gear shaper. Two operations are required to finish this part. The work is held in a magazine fixture rotating in harmony with the cutter. Note the shape of the cutter as compared to the shape of the part produced. This is an entirely different application of conjugate generating, where a cutter having two curved surfaces is shown generating a rectangular hole with sides differing considerably in length. The action of the cutter can be shown more clearly if we stop cutter reciprocation and rapidly rotate cutter and work. The cutter is set off-center in its holder and thus travels faster to finish the long sides than the short ones. When finishing the long surfaces, the cutter skids to make up for the difference in length of the long sides and the length of the arc on the cutter. This and preceding examples illustrate basic and special applications of the generating principle and demonstrate the versatility of the Fellows method. This presentation shows that the application of the generating principle is practically unlimited when a reciprocating generating tool is employed. The Fellows Gear Shaper Company cordially invites you to submit your problems for consideration.